Section 7.1, Introduction to Rational Expressions. Alright, so we define a rational number. So get our laser going. We define a rational number as a ratio of two integers, p over q. Okay, some p over some q, where q is not equal to 0. Some examples would be 2 over 3, where it's in the form p over q. It's 2 over 3, negative 1/5, and 9. In a similar way, we can define a rational expression as a ratio of two polynomials, p over q, where q is not equal to 0. So our polynomials we can put in fractional form too. Okay, so example 1 reads, evaluate the rational expression if possible for the given values of x. So when we read evaluate, let's see, I bet I can just, I have to write all this down. We're just going to snip this, actually. We'll just go together and then I'll snip it. Right. So when we evaluate rational expressions, all we're basically doing is plugging in some value into my expression. In this particular case, I'm a little tongue-tied this morning. There it is. I haven't spoke all morning, so this is fresh. So anyways, example 1. We'll just go ahead and snip it. We'll do it to current page. Yes. Since this page is really empty. Actually, we didn't even snip what we have to evaluate. Alright, so we are off to a little bit of a rough start this morning. That's fun. Alright, so when we evaluate expressions, all we're doing is plugging in that value that's being asked to evaluate into my equation. Okay, in this particular case, our equation is x over x minus 3. Okay, so if we plug in this value for a, where x is equal to 6, all we're doing is plugging in a 6 everywhere where you see an x. So this would become 6. Let's bring it down just a little bit. Let's go over here actually. This would become 6 over 6 minus 3. Okay, so again, all I'm doing is plugging in a 6 everywhere where you see an x, and that's what, 6 over 3, which is a 2. B, we're plugging in a negative 3, so we're going to have a negative 3 over negative 3 minus 3. And then this tons of negatives. And of course, nobody likes negatives, but they're not hard to go by or go through once you get used to them, right? So this is a negative 3 over, well, negative 3 minus 3, well, that's a negative 6. Okay, and a negative over a negative is going to result in a positive number. Okay, that's fine. So, and then 3 over 6, so that's 1/2. See? 0, this is a pretty easy one. So 0 over 0 minus 3. Okay. All right, so 0 over 0 minus 3, 0 over 0 minus 3. Well, 0 over anything is going to be just 0. And lastly, we've got a 3, so we've got a 3 over 3 minus 3. Okay, well, 3 minus 3 gives me a 0. Okay, so we've got 3 over 0, and we'll just go and write that out, okay, which we know is undefined. Yeah, which looks like a P, doesn't it? We'll just put UD, undefined, even though it's one word, right? Undefined. And that's it. That's all we do to evaluate rational expressions, or evaluate any expressions, really. Okay, so remember this, we see the avoiding mistakes, and we did that. Okay, restricted value. So real quick, and I might have given this spiel before, but everything that we learn in this course, you're going to be using in depending on what STEM, not, I guess it doesn't really depend on what STEM field. No, depends on what career path you're taking. You're going to be using this for every mathematics that you take from here on out. Okay, so don't think that we're talking about rational expressions and here we're going to be talking about restricted values and let it go in one ear and then out the other a week from now. Okay, because you're going to have to use this stuff for every mathematics course that you do use. This does build on top of each other. It's boring now, but I promise, depending on what sort of math classes you take, it does get a lot more interesting. But for now, that we do have to learn the fundamentals. So as boring as this might be in terms of I've heard this before, that's good. Just try to get it smash into your brain. That way you can remember this when you get to college algebra, when you get to pre-calculus, calculus. All right, everything that we do in this class, I promise you, is what my calculus students have trouble with, because that there are some things, some nuances that are forgotten. Anyways, go on. So restricted values of rational expressions. From example 1, we see that not all values of x can be substituted into the rational expression. We notice that we cannot plug in at +3, and that's what we say. Okay, so restricted values of a rational expression are values that make the expression undefined. That is, make the denominator equal to 0. So finding the restricted value, we're going to follow these two steps. We're going to set the denominator equal to 0 and solve the resulting equation. The restricted values are the solutions to the equation. Okay, will be the solutions to the equation that you create. The creation that you make is just looking at the denominator. And let's look at an example to see what that means, what we're talking about here. Well, B is easy. Okay. So A, what that said on the previous page was to create an equation. Okay, it's to create an equation with the denominator. That's it. Okay, so we're going to look at this. We're going to look at the denominator, and we're going to just set this denominator equal to 0. Why are we setting it equal to 0? Okay, because if we're looking at this problem right here, what could we not plug into this problem? All right, some of you could probably do this in your head. That's fine. All right, but what we cannot plug into this equation relies strictly on the denominator. Okay, we can put whatever we want to in the numerator. The numerator can be anything you want. The denominator can be everything but 0. So what we're going to do is equate the denominator equal to 0. Okay, and then of course the resulting equation would be y is equal to -7/2. And let's actually write that top over bottom like this. Okay, so -7/2. So this tells me that if I plug this value into this equation, then it would make the denominator 0, okay, because we said, hey, what makes the denominator 0? And that is my restricted value. That is the value I cannot use. I can use whatever other value I want to in the universe, right? But I cannot use -7/2 because it will make the equation undefined. Okay, now again, just kind of recap, and we'll see this when we actually start solving equations. We'll have some equation, x is equal to some y, and then we'll start solving. For right now, we just have expressions. Okay, so anyways, what was I saying? Nah, I don't know, whatever. Alrighty. Oh yeah, I got it. All right, so this is not the solution to that equation. Okay, this does not solve the equation. Especially if you have it equal to some number, right? This does not solve that equation. It's just saying what makes the equation equal to 0. What is the restricted value? What is the value I cannot use? That's all we're saying here. All right. B, we have a -5 over x. Well, this is kind of easy, right? Oh wait, no. That is the problem. We set the denominator equal to 0, x equals 0. Well, that's easy. X is equal to 0. Okay, so for b, x cannot be equal to 0. For a, y cannot be equal to negative 7 halves, right? And that's it. Restricted value is what it sounds like. It's restricted. It's a value that we cannot use. Okay, and of course we're going to step it up a little bit and actually get restricted values of rational expressions. Okay, so a, we're just going to look only at the denominator. Okay, so what is the restricted value? Okay, so I'm looking at the denominator. I'm going to look at a squared minus 25 is equal to 0. Okay, this one's easy because I know that a squared minus 25 is a difference of squares, so I can turn this into, well, no, we won't do that. I know that this can be factored into a plus 5 and a minus 5 is equal to 0, and therefore a is equal to plus, I don't know if we've done plus or minus 5 yet, got to that notation, but a positive or negative 5, or, you know, we could say that, in other words, a is equal to 5 and a is equal to negative 5. Okay, and certainly I'm sure some of you, most of you have probably seen this notation, plus or minus, just shorthand notation to not have to write both the numbers, positive and negative 5. But anyways, that's the restricted value of a. B, similar to the last example, is pretty easy. Okay, so now actually we'll work it algebraically and then look at it intuitively. Okay, so x squared plus 9 is equal to 0. And actually, just looking at this, we can look at it intuitively. We said that in the previous section, I believe, that we cannot factor a sum of squares. Okay, so we can't factor this. Okay, so that's fine. So let's proceed to solve for x. So we've got x is equal to the positive and negative square root of negative 9, right? Because we moved the 9 to the other side, and we take the square root of both sides. Okay, well, it's true we would have an imaginary number, but I don't think we've hit imaginary numbers yet in this course. So at this point, we're just going to say, oh, okay, well, you know, we don't have a restricted value for b. Okay, so no restricted value for b. And that makes sense though, right? Because if we were to look at this, all right, again, that's the denominator, okay? So what value when you square it, okay? So let's think about it. If you square any number greater than 0, it's a positive number, okay? Well, any number less than 0, well, that's also a positive number, right? Because negative 2 squared is a positive 4, negative 3 squared is a positive 9, right? So you're going to be getting a positive number. You take a positive number and then you add a positive number to it, well, it's going to be a positive number. Okay, and then of course, you know, I skipped 0, but 0 squared is 0. 0 plus 9 is going to be 9. Again, a positive number. So there is no number that when you add or subtract them together, that when you square them, will give you a negative 9 here to make that denominator 0. So that would just be kind of an intuitive way to go about things. We are going the wrong, there we go. Okay, this looks juicy. All right, so what is this saying? Simplifying rational expressions. In many cases, it is advantageous to simplify or reduce a fraction to lowest terms. The same is true for rational expressions. All right, that's true. The method for simplifying rational expressions mirrors the process for simplifying fractions. In each case, factor the numerator and the denominator. Common factors of the numerator and the denominator form a ratio of 1 and can be reduced. All right, so similarly to how this particular case here, we can factor, we know 21 is 3 times 7. We know 35 is 5 times 7. We can essentially cancel out those 7s, right, to get to 3/5. Now, this is very important here. The act of canceling, okay, and this is important for the end of this section. The act of canceling here does not make it just disappear. Okay, what it does is it turns it into a 1. It's just that, saying 1 times anything is redundant, so we just, don't write it. Keep that in mind because we're going to circle back to that at the end of this lecture. Okay. Same thing here. We factor the x minus 3's. Again, they cancel, right? But that canceling process turns it into a 1. All right, it doesn't just disappear. It turns into a redundant 1, and then we can proceed from there. All right, and then looking over here in the sandy area, the fundamental principles of rational expressions, it's basically what we just did here. Okay, the r over r, is what gets canceled. It essentially turns into a 1. It kind of, quote, goes away, but it doesn't go away. It's just a 1. Okay, it's just, again, it's redundant to say, so we leave that off. Oh, I forgot what we had to do. I didn't clip what we had to do. All right, so there we go. So A, factor the numerator and the denominator. All right, well, that's easy, right? So A, we're going to factor it. So the numerator looks like I can take out a 2. So we've got a 2, and what remains is a p minus 7 over, well, that's a difference of squares, so it's going to be a p plus 7. Try that again. And then a p minus 7. Okay. All right, so B, identify the restricted values. All right, so since we factored the denominator, we could set it equal to 0, right? We could say p plus 7 times p minus 7 is equal to 0. We could do that, but, we know that if we set it equal to 0, well, then we have p is equal to plus or minus 7, okay? And then C, if we were to simplify, all right, the p minus 7's cancel, all right, and again, they don't cancel in the purest form of the word, right? They turn into a 1, and again, I'm reiterating that constantly because the end is where we get a lot of mistakes. Hopefully we'll get there soon so I can stop rambling about it. So anyways, those p minus 7's cancel, so we end up with 2 over p plus 7. And that's it. Okay, this is something else. This is pretty important that we will circle back to later. I'm just going to put that there. It's true. We'll read it. The restricted value of a rational expression are always determined before simplifying the expression, and mainly because when we start solving equations, that's when this avoiding mistakes is going to really kind of go into play here. But let's leave that there and not ramble about it. Okay, right here. So in example 4, it's important to note that the expression are equal to all values of p that make each expression a real number. Therefore, we can reduce it down. For all values of p except for p is equal to 7, p is equal to negative 7. This is why the restricted values are always determined before the expression is simplified. From this point forward, we will write statements of equality between two rational expressions with the assumption that they are equal for all values of the variable for which each expression is defined. Okay. Let's see. Can I kind of dumb that down into any non-math terms here? No, not really. Alrighty, so let's jump to example 5. Okay, so simplify the rational expression. So now we've got variables on their own, powers of variables. All right, so many of you could probably do this in your head, and that's fine and good for you. But we're going to do this kind of a long way, and then we're going to do just a really quick way, okay? So long way first, we're going to write 18 like this. No, we'll do this. No, we'll do that. Okay, sorry, just thinking a lot here. We'll just write the 18, because many of you can determine that 18 over 9 does indeed reduce to 2. Okay, so we'll write 18, and then we'll write a times a times a times a over 9, a times a times a times a times one more a to grow on. Okay. All right, so we can tell, but when we write this out, okay, so this is a to the 4th, right? It's a 4 times, so it's a to the 4th. This is a to the 5th because it's a 5 times. But we can tell that we go cancel, 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 just like that. And this 18 over 9 would reduce to 2 over 1, right? Or, in other words, just 2. Actually, we'll put the 1 there. 2 over 1a, right? Or it would just be 2 over a. Okay? Now that's just that would be a way to go about it if you're having a hard time grasping powers, all right? But if you understand powers pretty easily, what I do, what I always just think of in my head is I would just look at, okay, look in here. Let's do a different color. Look in here. Okay, which power is largest? 4 or 5? Well, obviously 5, right? So we're going to go to the bottom. So it's going to be in the bottom, and then 18 over 9 is just 2, so 2 over a. Okay. So either way, however you want to go about it. Again, maybe this might be the easiest starting out, but the more you get into this, you'll just be able to look at it and tell very, very quickly. True. I didn't do it. I did not do it this way, but I'll snip this and put it on the problem. And we're almost done. I think we got 3 examples left. Okay, so this one, lucky for us, is a problem that we have to do a little bit of factoring on. So the first thing we're going to do, we're going to factor the numerator and the denominator. So we can, looks like we can pull a 2 out of the numerator, so we're going to have a 2, and what remains is a c minus 4. Okay, and the denominator, okay, so first thing we're going to do is take out a 10. We're going to make this a lot easier. Pulling out a 10, c squared minus 8c plus 16. Okay, all right. So look at the denominator. I can tell immediately because I've done this a long time, but I know also from the work that we've done earlier in this this course. What I do is I'm going to look at this and this, and I can tell right away that they are both indeed perfect squares, right? C squared, the square root of c squared is c, the square root of 16 is 4, okay? And furthermore, the square root of 16 would be 4, right? That is 4 times 4, but it's also negative 4 times negative 4, okay? And I know the negative 4 times negative 4 gives me positive 16, but I also know if you add them together, it gives me a negative 8, okay? So because of that, I know that this is a perfect square trinomial. So this can turn into 2c minus 4 over 10, and then c minus 4 quantity squared. Okay? And from here, I know that looks like I can cancel out I can cancel this c minus 4 out with one of those. Okay? So it's essentially, like saying, x over x squared. Okay, because it is a term, and I would be canceling out an x with one of the x in the denominator, except this time, they're binomials, right? So I can do that. I also see that the 2 divided by 10 is a 1/5, okay? So this is going to be a 1, and we'll make this a little bit, no, probably should have centered that 1 a little bit better. So I know it's going to be a 1/5, okay, and then what remained was a c minus y, right? No, c minus 4. Okay. And that actually wasn't so bad. It just it looked a little scary to begin with, but it wasn't too bad. Avoiding mistakes. What's this say? Given the expression, do not be tempted to reduce before factoring. The terms 2c and 10c squared cannot be canceled because they are terms, not factors. Yes. That is a big time mistake that gets made. Okay, so let's actually harp on this one for a second. All right, so again, given this expression, do not be tempted to reduce before factoring. The terms 2c and 10c squared, these two, cannot be canceled. They put in quotation marks too, right? Because they are terms, not factors. Terms being, numbers, variables, things like that, that are separated between addition and subtraction signs, okay? Factors are, we know ours as multiplications, right? It's this times this times all that, so on and so forth. We can only cancel out factors. The numerator and denominator must be in factored form before simplifying. This is huge. Okay. Many times I will have students say, or they'll do like x minus 4 over, let's do a plus, just, I don't like negative signs either, right? So x plus 4 over x plus 6, right? They'd be like, boom, we're done, 4, 6, 2/3, right? And that's not the case, okay? Because these are terms, okay? They are separated by addition and subtraction. They are not multiplied by one another. This is not x times 4 or x times 6. So we cannot do this. No. Okay? And might as well just, that looks kind of ridiculous. We'll just erase the whole thing. But anyways, this avoiding mistake is huge. You will undoubtedly make this mistake quite often if you're new to this, or this is a freshen up course. But hopefully you'll get out of that habit, because this is a very common mistake. So this is, oh, look at that. It's the kind of same example there. Let's do, all right, so this reads, the process to simplify rational expressions is based on the identity property of multiplication. Identity being 1, okay? Therefore, this process applies only to factors. Remember that factors are multiplied. For example, and we see our example here, 3 over 3 is 1, so we get 1 times x over y, which is here, which is have xy. Terms that are added or subtracted together cannot be reduced to lowest terms. This is basically what I said on the previous page, right? Except I used, I used 3 and a 4, right? Or was it 3 and a 6? Oh, I erased it. Whatever. This is essentially what I did on the previous page. kind of, right? This is again saying that we cannot just cancel the 3's, okay? Because they are termed and not factored. The objective of simplifying a rational expression is to create an equivalent expression that is simpler to use. Consider the rational expression from example 6 in its original form and in its reduced form. If we substitute a value of c into each expression, we see that the reduced form is easier to evaluate. Okay, and okay, so yeah, this is what we did on example 6 right here. This is our original equation. I mean, I even said, oh, this looks kind of tough, but we'll go through it. You know, you can plug in a 3 here, 3 here, 3 here. You can do all this. You can do all this. You know, you can do all this. You know, but nobody likes doing math with large numbers, right? And you would indeed get to the same solution, right? You know, this would be -2/10, which is still -1/5, right? You can get to the same solution. But if you do it in the simplified form, look how much easier that looks. This is why we factor. Right. Now on to what I've been kind of hinting at all lecture about, you know, we're not technically canceling, you know, that they're not technically going away. They are turning to a +1. And this is why. I guess I can put this right down here. Okay. So, when two factors are identical in the numerator and the denominator, they form a ratio of 1 and can be reduced. Sometimes we encounter two factors that are opposites and form a ratio of -1. For example, all right, looking at these examples, okay, -5/5 is -1, right? And also, 5 over -5 is equal to -1. Okay, we know this though, right? If we take any number and divide it by a negative number, you know, we're going to have a negative number, right? And we see that case for all of those. Okay, so they turn into -1s instead of a +1. We're going to see, you know, why is this useful? Heck, we'll just do it right here. All right, so looking at this, x plus 7 divided by -x minus 7. Notice how the denominator here is the exact opposite, the exact negative of the numerator, right? The numerator is a positive x, the denominator is a negative x. The numerator is a positive 7, the numerator is a -7. Okay, so if I were to do this, they would cancel out and create a -1. Because looking at this, in the denominator, if we factor out -1, that's what we do. That's what we're doing here. We factor out a -1 from this. We factor out -1 from -x minus 7. We see that we can, you know, essentially cancel the x plus 7s. So we'd have a 1 in the numerator, and then, you know, essentially this would be a 1 down here in the denominator, right? -1 times a +1 would be a -1, and then positive over negative gives me a -1. Same thing can be said here. Okay, so why is this important? Hang on. Avoid mistakes while the expressions are opposite, the expression are not. Okay, so yeah. So notice how these expressions, you know, because this is a +2, that's a -2. That's a -x, that's a +x. Okay, again, exact negative. The expressions 2 minus x and 2 plus x are not, because that's a +2 and that's a +2. Okay, they're not opposite signs. The x's are, but the 2's aren't. Of course, we know that as being a conjugate, right? But they are not opposite to one another, and therefore they do not simplify to -1. But anyways, like I said, why is this important? Well, let's see. Example 7. All right, so I can see right away that I'm gonna have to factor out a 3. So I've got 3, and then what remains would be c minus d over d minus c. Okay, so I look at this, and you know, something should be popping out right away. I see that the numerator has a positive c, the denominator has a negative c. The numerator has a negative d, the denominator has a positive d. Okay, so they are the exact negatives of one another. So what I can do, right, is I can cancel them. Okay, I can cancel like this, but make sure that whenever you cancel something like that, that you go ahead and make sure that you account for it by saying, times -1, putting that out there. Okay, whenever you cancel negatives, always account for it, just like this. Every time you can put it out front, put it behind, but always account for it. All right, and then we can continue. Well, what's left? We have a +3, and we've got a -1. 3 times a -1 is a -3. Okay, so always, whenever you factor to get a -1, always account for it by writing it out somewhere. Okay, so let's go back to a previous example where we didn't, right? So like this, we canceled this term with one of these terms. Okay, if we use the same process as with the negative, we could have said, times 1, put it out there. Okay, that's fine. But I mean, nobody obviously does that, but we are essentially doing that whenever we cancel terms that equal to 1. Okay, we don't have to do that for these. You don't have to say, times 1, times 1, times 1, times 1 for all 4 of these that you canceled. Okay, but for negatives, you always have to. Okay, oh no, which there will come a time, and probably in your homework tonight, where you might have to cancel 2 negatives, and you'll end up saying a -1, another -1 out here, and of course a negative times a negative is a positive, and it will influence the sign of the final solution. So whenever you cancel opposites, always account for it. I wonder if example 8 lets me do that twice. No, it doesn't look like it, but that's fine. And I believe example 8 is the last one. Okay, so simplifying the radical expression. Okay, so we got 5 minus y over, well, that denominator again is a difference of squares, so we're going to say y plus 5, y minus 5. Okay, so looking at this, my numerator has a +5, my denominator has a -y. Okay, neither of those are on the bottom. We don't have a +5 and -y on the bottom, so we can't cancel to form a 1, right? So instead, we're probably going to have to cancel to form a -1. So what's the opposite of a +5? Well, that would be a -5. What's the opposite of a -y? Well, that would be a +y. Okay, so what we're going to do is we're going to cancel this number, this number in the numerator with this number in the denominator. Okay, and again, we're going to say multiplied by a -1. We're going to account for it. Okay, and that's all that we're doing. So this in turn will be a negative, because again, it's this fraction times a -1, so it's going to be a negative fraction. All right, so we're going to have a 1 in the numerator and a y plus 5 in the denominator. And this is a little disjointed there, so we'll do it like that. Okay, so a -1 over y plus 5. And yeah, that does conclude the lecture.